So Gauss's law, I have a drawing right here. So if you have an arbitrary volume here, boom, and it's a sphere, V, and it's a sphere, and it has a surface and it's bounded by S, then it's the amount of charge inside the sphere is equivalent to the surface integral bounded by S of the electric flux density dot, which is the dot product, ds. ds is somewhere on the surface, like kind of like it used to is dA, the same as ds. And this just means that since V is arbitrary, then if you take V away, that means that let's say there was protons here, that means there's going to have negative electric flux. Now, what does that mean exactly? What does negative electric flux mean? Well, negative electric flux means that there's going to be electric charge coming out of it rather than inward, which would have inward flux. So, what does that mean for the proton? What does it state? That means that if you have an electric field for, let's say you have a photon, bing, boom, here we go, positive charge, and there's an electric field like this. Vector fields, we talked about this in coil and divergence, which I did a few days ago. And I placed it right in here. Then this photon will do its magic and turn this electric field into positive divergence. That means if Q, which is the charge, is positive, then that means that the divergence is going to be positive too. So putting this in differential form, putting this in a mathematical statement, it's going to look like this. The divergence of D, which is the electric density, is just dependent on Q for V in this example, in Gauss's law, as Carl Friedrich Gauss states it, the mathematician in the 19th century, and that is Gauss's law. So Gauss's law states that protons can make an electric field have a positive divergence, and electrons have a power to make an electric field with negative divergence. That's why when you see these dipoles, this little dipoles thingy, see that like this. They look like that. It's pulling the electric charge inward with the negative side and the electric charge outward on the negative side. So now that was actually, Gauss's law was actually the first equation of something called the Maxwell equation. Maxwell's equation set by James Clerk Maxwell, and there is that one, which is Gauss's law of electromagnetism. Two, Gauss's law electricity. magnetism. And we have Faraday's law. And 4. And Ampere's law. So we just talked about Gauss's law of electricity. Mom, can I talk about all 4 in one day?
Sure, go ahead.
Because they're really short. And now we talk about Gauss's law of magnetism. Gauss's law of magnetism states that one particle cannot be defined as the source of a magnetic field. So if you have this does not create a magnetic field. It does not. Unless it is like this, that creates a magnetic field. But if there's no electron there, it's like, sorry, electron. Then it does not create an electric field. It creates a electric field. It creates an electric field, not a magnetic field. And we know the divergence thanks to the first one, which is like positive. And the only sources of magnetic fields are dipoles, as far as we know, which have protons and electrons. And it goes like this, like I said in the other video, or not the other video, just 5 seconds ago. And it goes out this way. And that's the only way a magnetic field could survive. I mean, as far as we know. That's just what humanity knows. That's not. So magnetic monopoles don't exist. Oh no, I just got a solution. Break it in half. No, that's not what happens. If you break a dipole in half, it won't become a magnetic monopole. It'll just become 2. 2. If we break it in half again, both of them in half again, it'll become 4. If we break it in half again, it'll become 8. If you break it in half again, it'll become 16. If you break it in half again, it'll become 32. If we break it n times, it'll become 2 to the n dipoles. Dipoles! So there's no magnetic monopoles. No magnetic monopoles. That is Gauss's law of magnetism. Now Faraday's law. Faraday's law is very, very, very... Let's do Ampere's law first, before you get on to Faraday's law. Because Faraday's law is very long, so longest of all. So Ampere's law states that the permeability of free space times the current is equal to I can't believe I remember that. And what this means is that you have a wire. You have a wire, and the wire has a magnetic field. It's a potato. I mean, if I was trying to draw a potato, it would be look out. No, that's not a potato, is it? It's a potato. Okay, and it has like a little infinitesimally small vector that's dl, and the magnetic field is h, and the current is I. Magnitude of the current is I, and mu naught is the permeability of free space. So what does it do? What the heck does this thing do? What can it be used for? Well, it can be derived. It can be like this. It can be derived like this. get rid of the cross product, assuming that DL is parallel to H at any given point. So that becomes like this. Then you could pull H out of the integral since it is constant. Then you could evaluate the surface integral of the line integral dl, which will be just the circumference of that. So the circumference of h is going to be, let's say this is called k. It's going to be 2 pi k. 2 pi. And then we could divide by 2k pi. So we get ui over 2k pi. And then that's all. That's just for h. Or we could use it as an example. Or it's good to know for multiple reasons, because just plugging in some values for, or it's just like you could solve for k if you know the magnitude of the magnetic fields. You could just, that's k if you wanted to know k. These are useful for many things. And now, that was Ampere's law. Faraday's law. Faraday's law is, I need to get these papers together. Okay, so there's two types of Faraday's law. There's the Maxwell Faraday law, which is,
it's alright, Louie, it's just the dog.
Maxwell Faraday law, which is which we'll talk about later. And we have the Faraday's law of induction. Are you scratching close, Scooby? Oh, good job.
Louie, concentrate.
And we have Faraday's law of induction, which we'll talk about now. Faraday's law of induction. So let's say we have a surface like that, and it has a magnetic field. This. Magnetic flux, sorry. Not magnetic field.
Go play. I'm doing work because I gotta do my work. See ya.
Shh. And suddenly the magnetic field changed. Okay, it changed for two reasons. It could change for two reasons. And the magnetic field may change, or this may deform or just be moved. And it becomes like this. I'll say it was shrunk, it was deformed. Now it's only like this. Then that means a current would be induced in the wire. I know it sounds crazy, but it's true. Faraday, who was he? Michael Faraday found out. And a current was induced in a wire. So Faraday was experimenting with wires, and he found that this phenomenon can be measured with a magnitude, and it's defined as, well, you find the EMF of the wire, an electromotive force, and it is defined as technically that doesn't really matter because it's only, that negative doesn't really matter because it's only part of the Lenz's law. So we'll solve for Lenz's law at the end. We'll talk about that at the end. And to give an example of Faraday's law of induction, we'll get an example. We'll find that, let's say this is what here is 5 Teslas, and this right here is 3 Teslas. Right now we need to solve for the change in magnetic flux, d psi b. D psi b is what we need to solve for how many the magnetic flux of this right here. So solving for the magnetic flux, we have the magnetic flux density 5 Teslas, which is equal to B, and BA is going to be the magnetic flux of the whole thing. So if we have, because surface integral of B dot dA and multiplying that by the area is going to get us to, we need the dimensions for us. Let's say this is 2 and this is 5. 10 times 5 is 50. And we got that the total is 10 times 5, which is 50. 50 Teslas times meters squared. And this Teslas is Weibers over meters squared, square meters. Multiplying that by square meters would just give us Weibers. Let's just give it, 50 Weibers. That is our initial. And this one is 3 Teslas. The dimensions haven't changed. Oh, they have changed actually. The magnetic field didn't change in my scenario, did it? So 5T still. And let's give it 1 right here, 2 right here still. But let's give it 1 right here. 2 times 1 is 2. So this is 10 Weibers as our final. 10 Weibers minus 50 Weibers is negative 40 Weibers. We have negative over dt. Let's say the time interval over here is 3 seconds. No, 10 seconds. Over 10 seconds this happened. And negative 40 Weibers over 10 seconds. This is going to get us to our EMF, which is going to be, let's just take the absolute value for now because that's part of the Lenz's law. It's not literally a negative, which is going to get us to negative 4 volts, or Weibers per second is volts. And that is your EMF. So going back to the Ohm's law, V equals IR. So we need to have a resistance, don't we? Because everything has a resistance, no matter what it is. 2 ohms. 2 ohms. It has a resistance of 2 ohms. And to solve for the coolant, you can have V equals I equals V over R. So I equals, the resistance is 2, negative 4. I is equal to negative 4 over 2. That means I is equal to negative 2. That is your magnitude. Boom, bam, bada, ba. Now back to this mega design, you just use Lenz's law, which just states that using the right hand rule, the currents would be flowing get out your hands, stick it this way. Is the current flowing that way? Well, think about it. Put your finger right here and trace it upward. Well, that means it would induce a magnetic flux that would be going upward, which would be an additive, which would make which would make a magnetic field that would be upward. And then we have this endless cycle that would defy the conservation of energy. So that means it has to be this way. The magnetic flux has to be going this way. Let's see. Trace this. It's going down. Yeah, that works. Didn't defy. So that means it's going in this direction. And that means the current is going in this direction with a current the magnitude of -4. I'm sorry. 2. Not -2. It can't be going in a -2 direction. With a magnitude of 2 amperes. And that's the law of induction, but the law with the Maxwell-Faraday law is, let's say we have an oval like this, and it has a surface, a closed contour that's called partial sigma. And this is dl. It's an infinitesimally small length along the partial sigma. And it also has an area sigma. It's terrible sigma. Sorry, sigma. I'm going to do somewhat weird, very weird. And,
Was it an accident?
And it's like that. And what this states, Maxwell Faraday's law states, I'm almost done, but I know it's long, is that...
Come here, sweetie. Come here, sweetie. Come here. Here, this is really cool. You'll love this.
The closed line integral with the closed contour integral of well, technically it's actually negative.
Keep it on your eye so it doesn't swell up.
Well, this is the right here. It's an infinitesimally small. Instead of a vector, it's an infinitesimally small area. But in lots of cases, this is constant. So it just goes down to this, which is equal to V dot dA, which is just the magnetic flux, which is put that negative on the outside.
Well, you're hitting me right in the eye.
And that's the magnetic flux. Those two are equivalent in most cases, and in all cases, those two are equivalent. And that is basically just Maxwell's equations. But to evaluate this more, I know it may seem confusing. That's the electric field over there. So Lorentz force law, you know Lorentz force law. Lorentz force is electromagnetic force, and it states that the Lorentz force states that this is for electromagnetism, for Lorentz force, and so you know electricity and magnetism are related. So the electric flux entering here, exiting there, is equal to the negative rate of change of the magnetic flux entering here. That's all it's saying. With respect to time, that's all it's saying, like literally. So I think that was the simplest, but it's the hardest to understand. So it's really, really confusing. It's the shortest, but also the hardest to understand.
You're at 25 minutes, sweetie.
Oh, really?
That's fine. You could keep going if you want.
No, I'm done.
All right, say goodbye.
Goodbye.
Stay safe, everybody.